Thank you. Welcome everyone to the new year, the new academic year, and this is the first seminar of the year. And here we have Tesshu Hanaka, and he will present multi-agent pathfinding with crossing cost.
Okay. Thank you for giving the good opportunity to talk about this presentation. My name is Tesshu Hanaka from Kyushu University, and this is a joint work with Yuya Sekiguchi. He's our student, but he graduated last March. And also, yeah, Hirotaka Ono, yeah, also he's working for this. Okay, so before giving a presentation, I'll give some short self-introduction. So, okay, so my name is Tesshu Hanaka from Kyushu University, Fukuoka in Japan. So the Kyushu University is located here. So this is Japan, and so my university is located in the southern island in Japan, and I have some photo. Yeah, this is I think very beautiful my university photo. Yeah. So yeah. Anyway, so yeah, this is yeah. Okay. So and so my interest, my research field is mainly theoretical computer science, particularly graph algorithms, parameterized complexity, and algorithmic game theory. Also, yeah, I also working on the economic analysis using some economic data. Yeah, but yeah, today I'll focus on the graph algorithm or parameterized complexity part. Yes. Okay, so let me start this talk, and so in this research, so I want to think the multi-agent pathfinding. This is a very fundamental problem in multi-agent systems or AI fields. And multi-pathfinding problem, I call MAPF, is planning routes for many agents. Okay. For example, so if we have 5 robots in this directed graph, we want to find 5 paths for each agent. For example, like this. So this is a problem of multi-agent pathfinding. But when considering this problem, we want to minimize some costs. For example, the cost is defined by the length of passes, or another objective is minimizing the congestions of passes. But in this research, we focus on the crossing cost. So the motivation is as follows. So in path planning, if there are a lot of points where agents pass each other, then they have to pay attention for each other, which for avoiding the let's say corruption. Yeah. So which years are time loss? So for example, in this example, there are uh, 4 points agents go across each other. So we want to minimize the point. We want to minimize the number of crossings in multi-agent pathfinding. So formally, we can define these problems like this. The input is a directed graph and G equal V and K pairs of terminals S1 T1 to SK TK. So SI is a starting point and TI is a goal. And the task is to find K passes from SI to TI, minimizing crossings of agents. And so in this problem, we suppose crossings occur on bidirectional edges. And also the number of crossings for an agent on an edge is defined by the number of opposite direction agents. For example, so this example, so the crossings for this car is 3 because there are 3 cars from opposite direction. Okay. So in this problem, we first show this problem is NP complete in general. But if every edge of an input graph is bidirectional, then this problem can be solved in polynomial time. Also, this problem is FPT when parameterized by vertex cover number plus number of agents. Yeah, actually, so this is working in progress. So yeah, I want to have basic results, and so in this visit, so we try to expand the results. Okay, so let me explain the brief proofs of these results. And so the NP completeness can be shown by a reduction from 3 sets. Okay, so we first prepare the m pairs of terminals like this, and so SCI and TCI correspond to the pairs of terminals to the crosses. And we also prepare the bidirectional edges corresponding to the variables. And for example, so for positive literal of so if positive literal of variable x appear in the clause C1 and C2, then so we connect the SC1 to x and x bar to the C1, TC1, like this. And if negative literal of x appear in C3, then so we connect the SC3 to x bar and x to the SC3. So then, so if we choose and finally, so we merge the close vertices to the one one vertex, like one vertex. Then so if we set the variable true, then it corresponds to the set the direction from left to right. And on the other hand, if we set the variables to false, then so it corresponds to setting setting the direction from right to left. So then so yeah, then so we can show the 3 SAT is satisfiable if and only if there exists path planning without crossing. So this is a brief explanation of NP completeness. And for the polynomial time algorithm, so we can show this theorem. If every edge of an input graph is bidirectional, then MAPF with crossing cost can be solved in polynomial time. This follows from this fact. Any two connected undirected graph has an orientation making it strongly connected, and it can be computed in polynomial time from Robin's theorem. So if agents move along such an orientation, then no crossing happens. And if a graph is two connected, then so we have path planning without crossings. Also, if a graph is not connected, then crossings occur on bridges. So we can easily compute the minimum cost. So we can solve this in polynomial time. And so yeah, I skipped the FPT algorithm, but instead I introduced some open problems. So one open problem is this problem is FPT or not by only number of agents or only vertex cover or tree width. This is one of my big question. Also, another question is NP hardness on planar graphs and other settings. Okay, so maybe yeah. Okay, so yeah, I have additional slides, but also okay, it's okay.
Continue. See, switching.
Okay, so so we can consider the game theoretic setting in this problem. Actually, imagine that each agent selfishly want to minimize own costs. So the point is selfishly. So in this situation, we can consider these problems as a game theoretic problem. And to minimize own costs, agents can change their strategy. That is, change their routes to reduce their cost. So, and in game theory, we want to we want to check whether there is equilibrium or a stable solution. So that is the stability means that if any agent has no incentive to change their strategy, then strategy profiles, or which is the set of strategies, is called stable. And so the natural question is, does a stable strategy profile always exist in this problem? This question remains open, but so we if we suppose some assumption or restriction, then so stable strategy profile always exists, we showed. So the restriction is like this. An agent cannot change his strategy to a strategy using edges with opposite direction to used edges in his current strategy. So that is, so if we restrict the if we restrict the strategy agents can choose, then so we can show the existence of a stable solution. So, for example, so the restriction is like this, and so the an agent now so the current strategy of an agent is less one, and in this situation he wants to change the strategy, but we can't. So he can't choose strategy using the opposite direction of E. And under this setting, we show that stable strategy profile always exists, and finding a strategy stable strategy profile is PLS complete. Yes. So the conclusion is like this, and yeah, actually, so we have a lot of open problems for this type of MAPF. So if you are interested in this problem, please join us. Thank you very much.
Yeah.
So I wanted to ask, like, you asked about the first problem in planar setting, and my feeling was that your reduction from tree-sub, if you start from planar tree-sub, you would still have a planar instance, but Nikos.
No. We have discussed actually the reduction, and it doesn't seem like it because you created the copies.
We have to match the cross vertices, so it breaks the planarity.
You create two vertices for S and T. But for the same clause, you create two vertices and connect them with the clauses. So.
Okay, if you say so. And then, are you asking, or should I ask?
Okay, so I had a question regarding the. Thank you for the talk, by the way. Regarding one of your questions in the game theoretic setting, whether there exists a stable state, or what you call it, like equilibrium.
Mm-hmm.
So if you allow these strategies to be randomized, then according to Nash theorem, there should be Nash equilibrium.
I mean, my feeling is that whenever you choose a different route, the total number of crossings decreases, and it cannot decrease indefinitely. So there should be a stable profile.
Yeah.
So I'm sure the question.
The question is, they believe that it should always exist a stable profile,
Yes.
even in the general setting.
Yes, I believe. Yeah, but I cannot still prove that.
Okay.
Yeah.
If we don't have any other questions, let's again.